This is Lab 4, Magnetic Braking with Faraday by Frank Rogalon. The point of this lab is to get data on a magnet falling through an aluminum tube. Then it is to analyze this data and compare it to a computational model using the known parameters within the lab. And then it is to model it using GlowScript to see a visual representation and a graph. The final results was that the fall time was recorded as 0.722 seconds when averaging it on a 5 trial basis, and the simulated fall time was 0.687 seconds. As for the fundamental physics principles used, the first one is Faraday's law, as seen in the top right. This is used to calculate the EMF in each ring from changing magnetic flux as the magnet falls. Then the second equation, as seen in the bottom right, Ohm's law, is used to convert this EMF into current that will generate a magnetic field. Then, as seen in the third equation on the left for force, you can see the force of the magnetic carrying current wire, as shown there. And then the equation in the middle, the magnetic flux rate of a dipole, is used to simulate and compute the falling of a magnet as it changes flux through each ring. And then finally, the Faraday's law in the integral form, as shown in the bottom, is showing how the magnetic field is changing from circulating electric fields around each ring. Then the lab steps in this lab was to find the north side of a magnet, weigh the magnet, then record other important pieces of data such as the width, the length, and the radii of the aluminum tube. Then it's to drop the magnet through the tube 5 times and record the time using a stopwatch. Then average up those times and record it, and then put all this data into GlowScript and calculate it through a simulation. So the diagram on the right would be the free body diagram. The force of gravity is pushing the magnet down, and you can see here the magnetic force is being produced by the magnet. This causes an induced current going counterclockwise, and that creates a magnetic field from the loop that goes upwards to oppose it. As for the setup data from the experiment, I got that the mass of the magnet was 0.031 kg, the tube length was 0.351 meters, the tube width was 0.0167 meters, the thickness was 0.000518 meters, the resistivity was that, and then the inner and outer loops was these two measurements. The magnetic dipole is 5.22 amps per meter squared, as seen in the prior lab. And then as for the time, it's shown in this table, the average time for all the drops was 0.722 seconds. And then for the surroundings and the system was the magnet, and the surroundings was the aluminum foil and the earth, creating a magnetic field. As for the GlowScript code, what we have here is in the bottom right. This is all the inputted data. As you can see, the length, the width, the inner radii are all recorded pieces of data to create the tube. Then in the top left, we have other calculated factors such as the magnetic field at the ring, and then the force on the ring based on that, and then the force on the magnet based on the magnetic field. Then, as you can see here, the bottom left is the magnetic dipole, and this is a calculation used in the second lab. Just moved over to this lab to get the magnetic dipole. And then the calculated flux is this other written code here. Was shown in the prior formulas on the fundamental physics page. This was the results from the GlowScript. As you can see, the time was 0.687 seconds from the simulated time. When compared up to the experimental time, the difference is 0.035 seconds. Some of the possible errors when conducting this lab could have been that the stopwatch measuring time was inaccurate due to human error and not clicking it fast enough or stopping it fast enough. Then there could also be some rounding errors when measuring the tube for the length and the width and those factors. Any types of small rounding could possibly cause the calculation to go very far off. And then some other external magnetic forces, not just the earth or the aluminum tube creating flux. If there's anything else in the area that could have caused the magnet to slow down a little bit more as well. So if the resistivity on the conductor was closer to 0, how would this affect the dynamics of the magnet falling? If it was closer to 0, then the flux would be increased, which would cause the magnetic force to increase with its proportionality. This would cause an overall higher magnetic force, and the magnet would slow down in its descent and leading to more time inside the tube. And then if there was holes inside the tube, how would this affect the ring in the current model? the induced current would drop due to lower magnetic field. Lower magnetic fields would cause lower area, and thus overall the magnet would take less time to fall, decreasing the amount of time it spends in the tube.